Okay, good evening. Let's get started. Tonight, we will talk about another topic, is railway noise control. Why I schedule these topics at the beginning of this subject, because one of your group reports is relevant to railway noise control assessments. So that I need to share with you some general information and that you know how to do the assessments. So in the next two lectures, some relevant tutorial questions will be given in tutorial number 5 and tutorial number 6. Okay, so that you know how to do this one. You will form a group by yourself to select one of the assigned railway lines to do assessments. Okay, the information could be given to you later on, maybe in mid-October. So that's why I need to schedule these lectures before other topics. Actually, it's when you know how to do the railway noise assessments. The working principle is similar to road traffic noise effects, okay? Because both of the documents, one is what we call the assessment for railway noise control, and the other one is for road traffic noise control. Both of the documents were prepared and issued from the Department of Transport in the UK. The working principle is very simple. We just need to consider numbers of factors, and then add all of them together. We are able to find out the predicted noise levels to see whether you can fulfill the requirements or not. If you cannot fulfill the requirements, we need to do some further arrangements or to provide some mitigation measures. Even when you prepare EIA reports, our environmental impact assessment reports, we need to consider that if there are new very nice to be built surroundings or living environments, in that case, we need to consider, we need to make use of the documents, what I will share with you in the second half to do the assessments. Okay, so for the first one, for the first part, I just want to share with you some general information about that, what are the major sources to create very noise, and I will share with you some videos. Hopefully it can assist you to understand the working principles of that. This topic is very noise control, so at the beginning, we need to know how to, what are the major sources to generate the noise effects. Okay, before talking about how to do measurements or assessments, let me share with you some general information and backgrounds of railway transportations in Hong Kong. We could regard railway transportations, this is environmentally friendly options for large volumes of passengers, because you know that in Hong Kong, this is just a small city. We are with highly populated areas, so that's why the use of the railway transportations is one of the options every day. And compared with other vehicles such as aircraft, buses, ferries, or other heavy vehicles, it is more, you could not directly to generate pollutants effects, because we make use of electricity to drive train vehicles. So, but the problem is that when we increase the train speeds, it could enhance it could deteriorate the noise effects. In Hong Kong, we have 5 different rail systems. We can classify into trainways, MTR is the subway, okay, and we still have the lightweight vehicles, and we still have the expressway. Okay, so this is a general map under the subway system, and the total rail system length is about more than 200 kilometers, more than 200 km. And this is a map to show that we expect that this is the new developments of the metro train systems in Hong Kong in 2031. Okay, a few years later, some new railway lines are being built, and other ones, and we plan to build another ones to connect Hong Kong and Shenzhen. There are different standards to assess the noise effects, such as we could use the GB standard. GB standard is our national standard, and we have the UIC standard. UIC refers to the International Railway Union. When you compare them, we may consider the drive index and vibrations level, because these two parameters may affect the noise effects. Okay, more rigorous vibrations levels, may generate a louder noise effects. And when we assess the interior noise inside railway vehicles, we may refer to ISO standard, GB standard, and JIS standard. When you compare different standards, actually they are more or less the same. Okay, the standard, the requirements, they are more or less the same. We could not go through details about each one. I just want to share with you more detailed information for the railway noise control assessments in the second part of this lecture. So that sources of rail noise, this is the major source of rolling noise. What does it mean? It means that the interactions between the rails and wheels, okay, because you know that both are metal structures, okay, both of them, when they are in contact, it could create source effects. And the second one, this is the major source, and the frequency should be within 1 kHz. That means it is below 1 kHz, below 1 kHz. And this is the dominant source, okay. And you will consider rolling effects, rolling effects. This is the dominant one, and this is hard to reduce it, because you know that the rail is not always at a perfect status, okay. They may induce some imperfect status, such as corrugations. What is the corrugations? It means that you could, after a prolonged use of rails, you may induce some wave-like patterns on the surface of rails. Okay, because this is not a perfect status, so that's why when it is in contact with the wheels, okay, you could generate a noise effect, and this is what we call the rolling noise effect. The second one is the traction noise. It comes from the traction motors, gear, and auxiliary equipment. This is not the major one. Okay, the major one is this one, and the third one is impact noise. Impact noise can be generated at discontinuities and severe features in the track, such as ponds or corsets. I will explain to use that with ponds and corsets later on. And Welsh wheel, this one is high frequency noise. The dominant frequency is at 2 to 8 kHz. Okay, this is the friction effect. Okay, when you hear a high frequency noise effect, we can define this as the Welsh wheel, not the rolling noise. And the rumbling noise. What is rumbling noise? We may consider that this is the ground-borne noise effect. Ground-borne noise effect is a kind of structural-borne noise effect. It means that the noise effect that can be propagated through structures rather than in air. And this is generated as vibration form that can be transmitted through the ground structure and radiate some fields at low frequencies within buildings. Okay, so that if there are any structures, they are collected to railways, tunnels, okay, underground tunnels to the buildings. The generations of the rumbling noise can be transmitted through the connected structures to these buildings, surrounding buildings. Okay, this is an animation to show that under the dynamic effects of train vehicles, the rails could be vibrating in 2 directions. The first one is vertical directions, and the second one is the lateral directions. And noise wave data from bridges. The vibrations of the track is transmitted through bridges. When we use our bridges to carry train vehicles, we call this as a viaducts. Okay, this one. VIADUCT. Okay, viaducts. When a bridge is used to carry train vehicles, we call this as a viaduct, VIADUCT. And locomotive engine noise, we seldom use this type because we use electricity to drive train vehicles now, we seldom use this one. Okay, but we still have this one to carry cargoes rather than passengers. Aerodynamics noise, actually this one becomes dominant when the train speed is up to 300 km per hour. Okay, even the high-speed trains, how to define whether this is a high-speed train or not? When the speed is over 200 km per hour, we can classify this as high-speed trains. Okay, below that one, we cannot classify this as high-speed trains. To achieve the faster high-speed trains in China now is can be up to 350 km per hour. When we want to go further, okay, more than 400 km per hour, in theory we can achieve that. But in practical we could not achieve that. So that we have now developed the maglev type, okay, because the maglev type without the use of the wheels just follows the principles of the magnetic effects. We can achieve the speed up to 300 km per hour. Okay, before about that, we talk about the noise effects to the surrounding environments. Even inside the cabins, okay, some of them when you take vehicles, train vehicles in Hong Kong, okay, some of the portions could generate louder sound effects inside cabins, okay. And even there were some complaints in other countries, such as this one in the UK. Some drivers they complain that the interior noise is highly is really high, okay, up to 100 dBA. Okay, 100 dBA is very high level. Okay, so that's in general we can divide into different sources types to generate the railway noise. Okay, let me show you short videos about this one, railway noise. Actually, when you search it from the YouTube, you can find many relevant videos. Okay, in this video, the so-called real well noise is what we are talking about, the rolling noise. Okay, rolling noise. So when you come back to my lecture looks here, there's some sources. It is rather difficult to control it. The first one is rolling noise. Okay, below 1 kHz. The second one actually is the impact noise. Impact noise is a friction noise. Okay, high frequency noise could be resulted. And the third one is the well squeal noise. Is another difficult source to achieve this one. And rumbling noise actually this is not the airborne noise. This is ground-borne noise effects. And also in the video they talk about the aerodynamic noise. Okay, let us go through one by one later on. Okay, when we consider this is a typical section to show the components, the mechanical components on the train vehicles. We have a cabin to carry passengers, and we have the bogie. Bogie is a structure, a mechanical structure to support this cabin. In order to reduce the vibrations effects that can be generated from this cabins, the running trains to the supporting structure, we have two suspension systems. Okay, the first suspension system we call this one is the primary suspension. The primary suspension is to connect the track and the wheels, and the second suspension system is to connect this bogie to the supporting body. Okay, so normally we have two suspension systems. You may regard both of them suspension systems are spring structures, okay, to absorb vibrations energy. How to design and how to select an appropriate spring systems we will talk later on in the coming 3 lectures. And below this one we have a track, okay, and this is a rail. Our rail is I-beam structures, and they are slippers. What are the advantages of using slippers? These slippers, the main function is to attach the whole wheels on the ground surface. Okay, you can see that when you take a look on when you go to the home stations, you can find that some in the previously we used the timber structures as a slipper. Now we use the concrete structures to fabricate a slipper structure. Sure. So to control the noise effects, there are 2 ways. The first one is to reduce the airborne noise, and the second one is structural borne noise. The provisions of suspension systems mainly is to control the ride comforts of passengers and also control the noise effects. Okay, to enhance the safety of passengers, nowadays we install many sensing systems on trains, so that with the provisions of those sensing systems, it can allow us to monitor the operation status of the train vehicles. For this one, this is a video to show that how we can use our cameras to monitor the variations of the wheels and the track. Okay, you can see that now the train is moving on turning round. Okay, this one, so that you can see that this one, the straight line, if this line is directly on the straight line, it means that it is running on a straight way. Okay, there is variations now because the train is moving, is turning round. Okay, you can see that there is a deviations between the wheels and rail. Now it comes back to on this alignment, this straight line alignments. Okay, you can see this one because now the wheels and rails, they are on the same position. Okay, now the train is ready to turn another curve. Okay, you can see that there is a variations between the wheels and rail. Now we can monitor the deviations to see whether it can fulfill our requirements. This is the first one. This one is another one. This one is our department. They did monitoring studies on a metro train in Brazil before 2016 Olympics. Okay, we installed many sensors on the bogie because we want to monitor the variations and the status of bogies to see whether there are any problems. So we install the sensors here, and then we can conduct our real-time monitoring to see whether to see the signal variations here. Okay, when a train is when a subway is running, when a metro train is running, you can see that we can directly monitor the variations of the signals about the bogie. Okay, you may ask that what kinds of instruments we can make use of it to monitor the vibration system. You can install accelerometer. You may refer back to my lecture notes, the first two topics. In these lectures, I told you that we can use the accelerometers to monitor the vibrations of effects. Okay. So rolling noise is speed dependent. Okay, based on this simple equations, we observe that when you look at these equations, V naught is a reference velocity. When we increase the velocities, what happens? It means that the overall some pressure level could be increased. Okay, this one. So rolling noise is speed dependent. Okay, the faster the speed, the higher the some pressure level. This is a real situation. Okay, we cannot achieve this one. Okay, some particle issues and some particle examples in Hong Kong is that how to reduce the noise effects. Okay, let me show you the video again. In this video, I cannot find the English versions. I just find the Cantonese versions, but with screen tests. Okay, here, in this news report, they talk about how to reduce the rolling noise. Okay, although the speed reductions is not a logical ways to reduce this one. This is still a practical ways to achieve this one. Okay, because you know that it is not easy to build a new noise barrier along existing lines. Okay, because we don't have facilities or to retrofit new barriers along existing lines. This is not the money issue. This is the practical issue, structural problem. Okay, especially for wild ducks, the bridge to carry train vehicles. We cannot directly apply new barriers on the beach. You know that we need to calculate those structural noise whether they can afford or not. Okay. So that some portions, even in Hong Kong, and also not in Hong Kong, in other countries, they could propose the use of the reductions of space to achieve the standards to fulfill the requirements. Okay, three sources of rolling noise you could be this type of noise could be generated from wheels, rails, and sleeper. Okay, because sleepers they are used to support our wheel, and rails vibrations it depends on the excitations due to the wheel's rail roughness. Because you know that even we cannot directly observe the roundness of a wheel. Actually, after the use of this one, it could generate some polygons. Okay, even we cannot directly observe these polygons. In microscopic wheels, you can generate some polygons. We call this is the wheel roughness. With the presence of these polygons, you could create loud rolling noise effects. Impact noise, as I told you before, it could occur when a train passes through discontinuities on running surface, such as the rail joints, turnouts, or crossings. And Cheson's noise it is generated from power components. Actually, at very low speed, this becomes a dominant source, but at high speed, this is not the major problem. In terms of traditional wave traps, we have a form like this. This is a cross-sectional diagrams. We have two wells. Below the wells, we have a sleepers. All of these sleepers, they are used to attach and secure two wells on the ground structures. Below that one, we have some borders. Borders it refers to some small particles, okay, maybe stone particles. And below that, this is a subgrade or formations to support the whole structure. Trap forms, we may consider, in general, we may divide into four types. The first one is directly fixed type. The second one is boreless type. Boreless type is a common type, okay? Normally, we use this one before in the older days. And low vibration trap and the falling slab trap, I will explain to you the difference between these two types. This is a general figure to show the waves, okay? This is I-shape configurations. You can see why we use this one, not a rectangular shape, okay? Why? Do you know why? Why the current situations of using waves, all of them, they are in this form, I-type, I-shape, not in rectangular shape. So, this is relevant to structural problem, okay? Even in our buildings, we use the I-beams or H-beams to do constructions. They are relevant to the cost effects because if you use the rectangular shapes, the materials could be higher, okay? More materials should be used. But when we optimize the structure like this, I structures, you can reduce the material use and also you can make these configurations to support, to provide sufficient support to the dynamic loads above, okay? In addition to this type, some countries, they still use this groove type, okay, like this one. But very seldom scenarios, we could use this one. Normally, we would use this one before. And also, do you know what is the standard the separation distance between these two wells? Okay, the standard separation between these two wells is about 1435 millimeter. Okay, this is one of the standard approach. So when we go back to this one, this is I-beam structures. But when you compare the configurations for the head and the foot, the head is thicker than that of the foot. Pencil wranger. What is pencil wranger? Pencil wranger is this one, this mechanical components. To reduce the vibrations effects, some people, they invented this mechanical device, pencil wrangers, to secure it to absorb vibrations. But the results so that it is not good, it is not effective to reduce structural vibrations, the dynamic vibrations. Sometimes with the presence of these pencil wrangers, it could increase the vibrations effects. Okay, so that people, they make use of other approach is the well dampers. Well dampers. Why we need to use this one? Because the vibrations effects cannot be avoided, okay? With the when a train is in operations, it could generate vibrations. So that's we may make use of this damping system or damping device to reduce the vibrations effects. Okay, as I told you before, not only in Hong Kong, this reduction of speed is one of the practical ways to reduce the noise effects. Even you consider in the UK, because of the high, because the noise effects can be up to 109.5 dBs, okay, generated from metro trains. So that they still propose the use of the speed restrictions to reduce the noise effects, and they propose the use of the pencil wranger. This one to reduce the noise effects, but it seems that the effectiveness is not so good. Okay, this is the first type, directly fixed type. It means that we just put our wells, two wells on the structure. This is the simple type. And the second one is the boreless type. Okay, you can see that for this boreless types, there are many stones that can be used to support these structures. Another one is that for low-speed trains vehicles, the provisions of this ones can help to reduce some portions of noise effects because there are some air gaps between the stone particles. Okay, so that with the presence of these stone particles, it can help to absorb or trap the noise effects. But this is just for low-speed trains only. The third one is the low vibration trap. Okay, please take a look on this one. For this, in terms of this low vibration trap, on each wheel, you can see that we install rubber block under the base plate. Okay, this is the rubber blocks under this base plates. With the presence of this rubber blocks, it can help to absorb vibrations energy. Okay, so that less structural bond noise can be generated. Further, if we want to reduce further the vibrations effects, we may make use of this one, floating slab trap. For the floating slab trap, when you go to Mount Sinai, okay, they proposed the use of this one, the floating slab trap. What is the working principle of this one? You may refer to this figure. In this figure, you can see that if we do not impose any vibrations isolation systems below the dynamic effects, you can see that all the force can be transmitted, correct? If we just install some spring systems below the system, we can reduce certain amounts of the vibrations energy. If we use concrete pith in combining with these spring systems, we can further reduce the vibrations effects. The working principle of this floating slab is like this, okay? We install a concrete pith or a concrete mass. And then below this one, please remember, not only we just put in a concrete mass, and also we need to install isolation systems below this one. Okay, otherwise, it is similar to a structure, and the force can still directly go through the structures to the surrounding environments. So when you compare the low vibration trap and the floating slab trap, there are two diagrams here. The first diagram is that we just put an isolator below each well. And in the floating slab trap, we just design a structure, a floating slab, and then below the concrete slab, we still install isolators. Okay, so that this is the major difference between the low vibration trap and the floating slab trap. And there is a term here, the colons. This is a device, a mechanical device to attach two wells on the structure only. Okay. Okay, in another way, we can define the trap forms, bolus types or non-bolus types. Okay, in terms of the bolus type, like this, like the figure here, the major advantages is that it is relative low construction cost. Okay, in the past, when I asked students to define the difference between the bolus type and non-bolus type, most students just told me that bolus type has relative low cost. This is not correct. Okay, you have to identify no construction cost only. The operations cost is still high. Okay, so if you just say that this is low cost, it is not fully correct. Okay, so and high elasticity because we just use the bolus materials to support the structure, so that in terms of the lateral movements, it is under high elasticity. And high noise absorption, it is just for low speed train vehicles only. Okay, not for high speed trains. There are still disadvantages such as the limited lateral resistance in curve, and bolus particles may be disturbed up to cause damage of wheels and trains. How about bolus type, non-bolus type? You can reduce heights. What does it mean? For the first point, when you go back to this one, okay, when you go back to this one. This is a typical section to show the bolus type. Okay, when we design a non-bolus type, we can remove this part. We can remove this part because we don't have bolus materials here. So that's why the overall heights of the whole the track form structures can be reduced. So the first point is reduce the overall height of the track form. The second one is low maintenance and with high availability. You can increase service life and higher lateral resistance. The major disadvantage is that we need to invest more money, but with no lower maintenance costs. Okay, this figure I extracted from this mechanical vibrations, ground bore noise, and vibrations from rail systems. There are different trap forms we can design, okay, such as the bolus type, and also below the bolus types, we can install some rail packs, and these rail packs can be able to support and absorb energy. Okay, ground bore noise. Ground bore noise is a kind of structural bore noise when a train movements are inside tunnel like this one. Because of the vibrations effects, the low frequency vibrations can be transmitted through the connected structures to the nearby building. Okay, like this one. And inside the buildings, you could re-radiate low frequency noise to interior areas. It is so annoyance. Okay, and the low frequency noise should be in the range of 30 to 250 hertz. Remember, low frequency noise is a kind of it's not a good thing. Okay, it could make us discomforts. And although we are not sensitive to low frequency noise, the effect is still existent. Okay, so that's why we need to consider how to reduce this one. To reduce this one, we may use the fallen slab track. Okay. In this topic, I could not go through too much details about the vibrations isolations because we still have 3 lectures to go through these topics. I just want to share with you that how to calculate the electrical frequency of the system. When we consider that the scenarios of the train vehicles is similar to a mass, okay, a simple mass, okay, under the dynamic force, this is a force, and with the support of a track, okay, we can classify into this is the stiffness and also C is the damping effects, okay, so that we have 3 components only, correct? M, K, and C, okay, in this figure. How to calculate the natural frequency? Okay, you may update your lecture logs here, okay, state that this is the natural frequency, and also this is what we call the resonance frequency. I will explain to you why both terms are okay. Okay. When we simplify the scenarios to a single degree of freedom system, okay, in this subject, we just focus on a single degree of freedom system. What does it mean? It means that we just consider that there is a mass, K, and the damper, okay, 3 components only. We could not go to study multi-degree of freedom systems, okay? For this one, you can see that to find out the natural frequency of a system, we follow these equations, is K over M. Remember, frequency here is in terms of hertz. The unit is in terms of hertz. Okay, why I stay here, natural frequency is equal to resonance frequency. Okay, how to achieve resonance? When the external frequency, when we apply a force to this system, okay, we call this external frequency, correct? Okay, when we apply an external force on the system, when the external frequency is exactly equal to this natural frequency, resonance could occur. So some people call this natural frequency. Another name is resonance frequency. Okay, let's say the natural frequency of this system, okay, let's say it is 10 hertz. If the natural frequency is 10 hertz, when we apply an external force on this system and the external frequency is also 10 hertz, okay, resonance could occur in this case. Okay, do you still remember what is resonance? Okay, resonance could make the system, the motions of the system amplified. Okay, we can increase the vibrations effects of a system. Okay, similar to this one. Similar to this one. Okay, when we drive this grass into vibrations, okay, finally we could achieve breakings because the resonance effects. Okay. So here I just want to introduce these equations to you. How to do calculations I will introduce to you in the next lecture. Okay, in this one, how to read this figure? We want to reduce the transmissions of the force that can be transmitted through the structures to the surrounding environments, so that transmissions of force can be reduced at higher force frequency. Broader frequency range of vibrations can be isolated by lowering electrical frequency of the track form. How to read this one? When you consider this one, okay, this is the transmissibility. What does it mean? It means that this is the ratio between the transmitted force to the driving force. The driving force is here. Okay, you may regard this is an external force. Okay, applied on this system. Okay, what is the meaning of 10 naught? It is equals to 1, correct? Okay, 10 power naught is equal to 1. Along this line, it means that okay, we have 2 forces. The first one is the transmission force. Another one is the external force. If you consider that this is a simple structure with damper and with mass, okay, if you apply a force on this system, and Ft is the transmitted force to the surrounding environments. The case here, we want to reduce the Ft. We want to reduce the transmitted force. Okay, if we can control the transmitted force, it means that we can control the structural bond vibrations, correct? Okay. although we apply an external force to the system, if we do not have any force that can be transmitted to the structure, if Ft is equal to 0, okay, it means that we can well control the dynamic effects, correct? Okay, so when you take a look on this figure shows that this is when the ratio Ft to F is equal to 1. What does it mean? It means that when you apply 10 Newton force on this structure, it means that 10 Newton could be transmitted to the ground floor, correct? So we want to make this ratio as small as possible, So how to decide this one? We want to go to this region, correct? In this region, all the ratio is below 1. Below this one, about this line, it means that all the ratios, they are higher than 1, okay? We don't want to go to this one. This region, we call this region is the regions of amplification. And this region, we call this one is isolation region, okay? So how you can see that when the external force is equal to the natural frequency here, resonance occurs. This is the resonance, okay? You can see that there is a peak here. This is the resonance effect. Okay, when the external force is exactly equal to the natural frequency, at that time, resonance occur. We don't want to have this one because let's say you can see that if we achieve to this one, the ratio is 10. What does it mean? It means that when you input 1 Newton to the system, when you input 1 Newton to the system, the results could be 10 Newton. Okay. So we want to go to this region, not in this region. Okay. I repeat again. When you refer to this figure, we just simplify the scenario like this. Okay, we have a mass. And we have a, okay, you may refer to this one, this figure. Okay, we have a mass. This is the external force, and we have Ft. Ft is the force transmitted effect. And driving force, we refer to this F, okay? When we design a system, we want to achieve the situations to this region, because at that time, all the ratio Ft to F is below, this is below 1, okay? That means we can reduce the ratio, we can reduce the effects. When the ratio is more than 1, like this one, it means that we amplify the situations. More force, more amounts of force can be transmitted to the system. This is not what we want to achieve. Okay, P2 resonance, what is that? P2 resonance, this is a simple harmonic motion when the wheel sets and the wheels, they are working together in phase. They are vibrating in phase together on elastic support. Normally, it could happen at low frequency, 30 to 100 hertz. We are talking about the impact force, okay? When a train is running on a rails, okay, impact force could be generated. Why we call this is P2 force, because we still have P1 force. P1 force is at high frequency, so that we don't care about this one, high frequency. And the operations time is in short durations than that of this one, P2 force. P2 force is under low frequency, 30 to 100 hertz. So that's why we care about this one, because the major structural bond vibrations effects is come from P2 resonance effects, okay? For this one, let us go to how to calculate the natural frequency in the next lesson. Okay, here I just state the equations first. And I mark remarks here. P2 resonance. Actually, this is a phenomenon that we call this as P2 resonance. Is the in-phase bounces together when vehicles unbound mass in relationship to the stiffness. There is a term here. Vehicles unbound mass. What is this one? Some people they define keywords about what is the unbound mass and unbound mass. Unbound mass it refers to the wheel sets connected. Is the mass connected to those wheel sets, but it is not related to the suspension system. It's not related, okay? If it is related to the suspension system, we call this as unbound mass, okay? Not the unbound mass. Okay, in terms of, because the metro train, the speed is about 70 to 110 km per hour. When we consider this simple equation, F is equals to V derived by lambda, okay, you consider P2 resonance occurs at about 30 to 50 hertz. What is the lambda? Lambda is the difference between these two slippers. The difference between these two slippers is about 600 millimeter. So when you change 70 km per hour in terms of meter per second, okay, it means that when you use 70 derived by 3.6, we can calculate the speed in terms of meter per second. And lambda here is, you can change it to 0.6 meters. The result is within this range. Okay, while that is a kind of bridge structures, they can carry train vehicles. This is a real case in Hong Kong. The Westwell phase 1 is about 30.5 kilometer. In which 13.4 kilometer alignment is on the wild ducks. As I told you before, one of the noise sources is from bridge noise. In order to reduce the noise effects, okay, on the wild duct, they make use of two approaches, one for airborne noise and one for structural borne noise. For airborne noise, they install some absorbing linings materials here, shown as yellow color here. And you can see that because the provisions in the Westwell in long sections here, they make use of the folding slab track. This is a folding slab, okay? Be careful. The provisions of the folding slab is to reduce the structural borne noise, okay, not airborne noise. The provisions of these barriers, absorbing linings materials, they are used to reduce the airborne noise effects. And this is another example to show that this well ducts, we use the noise barrier, fully enclosed barrier, and also below this one we install the spring isolators. Please pay attention to this one. The provisions of spring isolators, it is used to reduce the structural borne noise, and the noise barrier here is used to reduce the airborne noise. We still have other mitigation measures to reduce the noise effects, such as we use the resilience wheel. In terms of the design of the resilience wheel, we install some rubber rings inside the wheels to reduce the vibrations effects. We also use the damped wheels. And I told you before, normally we have different products in the market about the wheel dampers. What is the wheel dampers? Normally they make use of working principle is the TMD, tune mass damper. What's the working principle of tune mass damper? When you go to Shanghai Tower, the high-rise buildings, and 101 Taipei Tower, okay, when you go to the top floor, there is a very large mass, okay, the tune mass, okay. It means that under the wind effects, okay, when the building is in this direction, the damper could be in the opposite directions to resist the rotations, the vibrations of the building, okay. This is what we call the tune mass damper, a passive tune mass damper, and we impose the we apply this simple principle into the wheel damper here. Under the operations of the trains or the vibrations effects, this simulation shows that this animation simulation shows that the vibrations of wheel. And when we install wheel dampers along both sides of the wheels, okay, you can see that if it is in this directions, the dampers is in the opposite directions to resist the directions. So that at least we need to design a system that can be working in two different directions. The first one is vertical one, and the second one is the horizontal one. Okay. Okay, in this video, you can see that when we apply wheel dampers on the wheels, what could happen? This is the speed, and one is on a straight track. This is curved track. You can see that the noise effects could be significantly increased. Now, when it passes through the damper sections, the noise effects could be reduced. Okay, I will play again. Okay, these sections without the provisions of any dampers. Okay, when it passes through the damper sections, you can see that the noise effects could be dropped significantly. Okay, in the market, there are different products for wheel dampers. Normally, the effectiveness of a damper can be reduced the noise effects up to 3 dB. Okay. It depends on different products. And in Hong Kong, there is a local company, is what we call the Wilson Acoustic. They invented multi-tuned mass dampers. They propose that it can reduce the vibrations 10 dB, not the sound effects 10 dB. Okay, please pay attention. This is the 10 dB vibrations reductions, not sound effects. When we install dampers on the track for testing, you can see that the red line is the original results, and the green line is that when we apply these dampers, you can reduce 3 to 4 dB, okay, under 800 hertz. This is one of the advantages of using wheel dampers. Another one is that when a train for a long duration use, it can induce this pattern. Okay, this is what we call the corrugation. This is similar to a wave-like structure. With the presence of these corrugations, it could enhance the noise effects. Okay, because this is not perfectly smooth. But when we install some dampers along some sections, they found that it can reduce the formations of this corrugation. Not only reduce the noise effects, and also you can reduce the presence of corrugations. What made the presence of corrugations? Vibrations energy. Okay, you can see that under the continuous operations of trains, the vibrations energies could be transferred to a track. Okay, and sometimes you could miss the periodic wave-like structures like this one. This is the corrugation. This is the major effect to induce rolling noise. So after a period of time, we need to do the wheel grinding to reprofile this wheel into a perfect status. How to do this one? This is the wheel grinding. We can make use of this one to reprofile the surface of wheels. Okay, we move the corrugations. Okay, but we normally do this ones for regular periods. Okay, maybe several months. Okay, we still have other types of mitigation measures, such as we use the lubrications, put it on the surface. We use the undercar plenum like this one. This is a small scale barrier, This some people call this is the undercar plenum or the skirts. This is the skirts. Noise barriers are common form. We use this one. When you want to take a look on the bogie, you can go to our industrial center. We have a 1:2 ratio 3D printed bogie here. And some people, they did a research to study the contributions of different train parts to exterior noise at 350 km/h. When we derive into different components, you can see that which parts can generate the higher exterior noise effects. Yes, the bogie, okay, 32%. Bogie is here. So, well, we need to pay attention on this one, bogie. And there are some other general information. There are some general statements about that. The characteristics of train-induced vibrations, such as the axial nodes, geometries and compositions, the speed of train, and the wheels and rail interface. If there are any defects, it could induce the noise effects. I could not go through details about that because I already presented before. And this is the figures to show that the roundness of a wheel. Originally, you can see that the blue line, original is a blue line. After a period of time, you could induce some polygons on the surface. So that when you compare the red line and the blue line, you can see that in terms of the roughness levels, it could be increased by 39 dB. This is not the sound level. This is not the sound level. This is the roughness level. And also irregularities or the variations of the support structures can also induce the train vibrations. Okay, many trains. The working principle is simple. We do not make use of wheels. Although we do not use wheels, it doesn't mean that we do not have vibrations. Okay, you still have the vibrations effects. It depends on the the magnetic levitation techniques, the speed can be more than 400 km per hour. They are high speed, very high speed maglev, such as in Shanghai, the top speeds can be up to 431 km per hour, and the fastest in the world is in Japan, can be up to 603 km per hour. Normally, we still have some low speed maglev trains in China. Okay, I summarize some of them, some of the examples here in China, in Japan, and in Korea. For the magnetic trains, there are two working principles. The first one is the electromagnetic suspension trains, and the second one is the electrodynamic suspension trains. One, it depends on the reflection attraction effects, and the other one is due to the repulsive effects. Okay, this is another project we did before for the monitoring of the magnetic train. Okay, before talking about how to do the assessment, before the break, I want to ask you a final question: is that to design magnetic train vehicles, do you think that the head is more important or the tail is more important to reduce the aerodynamic noise when you design a train? Okay, like this one. Under very fast speed conditions, do you think that this one should be a streamlined design is more important at the head sections or at the tail? Which one do you think that is more important? Head, tail. Tail is more important because turbulence effects could be formed at the tail sections if you do not have a very specific or a smooth design. When turbulence occurs, it could generate a higher aerodynamic noise effects. Okay. Okay, let's take a break for 5 minutes and then we go to the second part. The second part is talk about how to do the assessments for railway noise. Okay, let's get started. Okay, in this part, we will move to another topic is how to do the assessments for railway noise. You know that when we do, let's say when we do environmental impact assessments or when we want to predict noise levels based on the current situations, we may make use of this approach. How to do this one? Before talking about that, let us go through what are the legal requirements for railway noise. When you go to, let us go look at this figure. This figure. Okay. In the first two lectures, I just show these two columns to you when I talk about the noise exposure forecast. Now, when you go to the railway noise, this is the assessment criteria for very noise. The equivalence level for 24 hours should not be more than 65 dBA, and the maximum level during the 11 o'clock in the evening to 7 o'clock in the morning should not be more than 85 dBA. Okay, still remember that when I placed the video, the speakers told you that we could make use of the equivalence levels to do assessments. So that's why it is not difficult to fulfill these requirements, because how to do the how to calculate the equivalence level. This is the way we can find out. This is the figure to show that the equivalence level. There is a term here, AEQ. It means that we apply the A weighting system to these assessments. Okay, please bear in mind these two requirements. To assess the noise level, very noise level, we have I told you before, we have several technical memoranda. To assess the very noise, we may refer to the technical memorandum for the assessments on noise from places other than domestic premises, public places, or construction sites. And when you refer to the technical memorandum for EIA process, they could refer to, they identify a simple ways to do the assessments. The basic procedures is like this one. We do the measurements to get the noise level, and then we can identify whether this is an impulsive noise, intermittent noise, or tonal noise. For the tonal noise, in the last lab, I told you that how to make use of the technical memorandum to do the assessments. And then we do the corrections to find out the overall level. On the other side, we need to consider that the types of area, influencing factor, whether this is ASR. What is ASR? Area sensitivity rating. Any buildings, no matter this is educational building like us or domestic buildings, office building, we can classify they are areas. They are area sensitivity ASR. ASR. And the time of day is that. Okay, I'll repeat again here. On the other side, this is we need to consider the types of area and then the influencing factor. How to find out this one? We may make use of this figure. In this figure, the vertical column here is the types of area containing NSR. What is NSR? NSR is the noise sensitive receiver. NSR. This one, NSR is noise. Okay, noise sensitive receiver. NSR refers to any buildings. Okay, no matter this is office buildings, commercial buildings, industrial buildings, or educational buildings. All of them, we can classify this as noise sensitive receivers because there are people inside for doing any activities. If the NSR are located in rural area, and we have three categories. The first one is not affected. The second one is indirectly affected, and the last one is directly affected. We have A, B, and C. Okay, A, B, and C. The values for A, B, and C, you can refer to this one. Okay, A, B, and C. The ASR, the area sensitivity rating, or the acceptable noise level should be, the lowest one should be for A is 60 during the daytime, for B type is 65, and for C is 70. Okay. We can identify where is a rural area or where is urban area. For example, when we are talking about Hong Kong, our campus, we cannot define this as a rural area. We have to decide this is an urban area. But the problem is that especially for those urban areas, whether the scenario is under not affected, indirectly affected, or the final one directly affected, it depends on real situation. Okay, so that's they do not have a very specific definitions for that. Okay, if the noise effect is just nearby or adjacent to this building, okay, you cannot classify this as indirectly affected. Okay, it doesn't make sense. It depends on the real situation. And then you can compare the acceptable noise level and your calculated noise level to see which one is higher. If the corrected noise level is lower than that, or the acceptable one, it means that no any further actions we need to take. If the corrected one is higher than the acceptable noise level, the authority could issue noise abatement notice to you. This is a warning notice. Okay, that means you need to do some appropriate actions in such a way that to reduce the noise effects. Okay, this is our main target. We want to study this one, the calculations of very noise. This document was issued in 1995 from the Department of the UK to assess the very noise. Although this document has been published more than 20 years and almost 30 years, the approach proposed in this document is still valid. We could make use of this one. At least in Hong Kong, the authority could make use of this one to do assessments. And other similar predictable models from other countries, they are similar to this one. Okay, how to do this one? Actually, the working principle is very simple. Let's go to this one. This is a flow chart to show how we conduct 6 stages to do predictions. The first one is to divide variables into different segments. Okay, the second stage, I could explain to you one by one. The second stage is to find out the reference noise levels. It depends on the numbers of vehicle and the track form. The third one, it depends on 1, 2, 3, 4, 5, and 6 parameters. Okay, distance corrections, air absorption corrections, ground corrections, and up to angle wheel corrections. And stage 4 is reflection effects. Stage 5 is to convert sound exposure level to LAEQ. Why this one? Because please pay attention. At stage number 2, we need to find out the sound exposure level. But what is the legal requirements for very noise assessments? LAEQ. So that we have equations to convert sound exposure level to its corresponding equivalence level. And finally, we have to calculate the overall levels. It depends on stage 1 whether we have different segments. If we do not have different segments, we just need to we just can conclude that this is the overall result. Okay, stage 1. Whether we need to divide variable into one or more segments, it depends on several scenarios or several suggestions, such as the traffic flow, train speed, gradients of track, progressive variations of swinging effects. Please go to this one. In this document, they propose a number of points. If we encounter one of them, we need to derive into different sections. Okay, let us take a look on this picture. The first condition is that where the variables runs in a cutting along part of its length. Let's say this is a single track, okay, and this is a double tracks, one is in parallel. When you compare this section and this section, we need to derive into 2 different segments because at the upper part we have 2 parallel tracks, but at the lower part we just have a single track. You cannot directly assess the whole tracks together. Okay, you have to derive into 2 different segments. Any problem? Okay, this is the what is the points for the first one. The second one, where there is a skewness to parts of the railways or where the degree of skewness changes significantly over the length of railway being considered. It means that if there are barriers along some portion, we still need to derive into different segments. Let's say if this part we have a barrier, but this part we do not have a barrier, we need to further derive into different segments. Okay. The third one is that where the one-way runs on a wire dot or other constructions which could make significant changes to the noise effect, we still need to consider that the divisions of multiple segments. Okay, it means that if some portions the train is running on the wire dots, but some portions the train could not be running on the wire dots. In that case, we still derive into different segments. Okay, and the third one, where the speed of passing trains changes significantly over the length of railway. If there is a change of the train speed, we still need to consider that whether we need to derive into different segments. At junctions, at points, what is points? Please pay attention to this one. Please look at this one. This is a point. In terms of railway engineering, point is a mechanical switch to divert the flow. Okay, when you turn this point from this direction, we can go to this direction. Okay, so that's points in engineering. In railway engineering, it refers to mechanical switch. Okay, this is causing. So that when we consider like this one, this track, okay, there is a point here. We may consider that this is the first segment and this is the second segment. So they just list out a total number of conditions that if we encounter one of them, we may consider that we have to derive into different segments. Okay, this is the first stage. Okay, any problem about the first stage? For the second one, calculate the reference noise level, SEL. Normally, in reality, we could put a microphone 25 meters away from the rail tracks, the nearest track, okay, to find out the sound exposure level. Calculate the single vehicle for different types of trains. What is the millions of single vehicles? Okay, let me show you not a beautiful figure like this. Okay, when this ugly picture represents our real trains, okay, each train has different vehicles. This is what we call the single vehicle. That means our single trains composed of many vehicles. We need to focus on a single vehicle first. When this vehicle is used to carry passengers, we call this one is coach. When it is used to carry cargoes, we call this is wagon. Okay? We call each one, this one, okay, is a single vehicle. So that a single train, it may consist of multiple vehicles. When you refer to this one, this is chart A1.1. This is for rolling railway vehicles. At that time, we still make use of two types of vehicles. The first one is driven by electricity. If it is driven by electricity, the major source is from rolling noise. The major noise source is from rolling noise, and we call this is the rolling railway vehicles. And the other one is locomotive type. Locomotive type is driven by diesel power. Okay, we have two types. Remember, when you refer to these documents, we have two train types. The first one is the rolling type. Rolling type means that the major dominant noise source effect is from the rolling noise, and it is driven by electricity. Okay, when you take a look on chart A1.1, this is the sound exposure level, and this is the speed. Let's say if the speed is 80, the sound exposure level is here, is about 69. Okay, 69. The unit is in terms of dBA. You can make use of these equations or these charts to find it out. You do not need to memorize all these equations. Okay, all the equations could be provided in your final examinations. I just want you to I just expect that you can make use of the appropriate equations to find out the results. Okay, not to memorize those equations. Okay, this equation is exactly the same as you find it from this figure. You can check it by yourself. V here is in terms of what? Kilometer per hour. Okay. So please pay attention. This chart A1.1 is just for rolling railway vehicle only. If in the questions, they state that this is a locomotive type, you have to refer to chart A1.2, not A1.1. Okay. In A1.2, when we increase the speed, you can see that the sound exposure level could be decreased. Okay. Any problem about A1.1 and A1.2? Okay. Now we go to this one, and then when you find out the sound exposure level for the single vehicle, now we need to consider the types of vehicles. Okay, there is an equation here. The reference single vehicle sound exposure level is equal to baseline sound exposure level. The value here, you can get it from chart A1.1 or A1.2. Okay, it depends on whether this is a rolling type or a locomotive type. And then you still need to consider the correction factor in table A1.1. For table A1.1, it depends on the vehicle descriptions. Okay. I extracted this table from the documents. Some of these vehicle descriptions are not up to date, but it doesn't matter because I just want you to understand the working principle. Okay, let's say if this is a British Rail MK2 type, the correction factor is 14.8. So you select this correction factor and put it here. You can find out the reference single vehicle. Okay, any problem? If this is a locomotive type, let's say class 33, the correction factor is still 13.8. It depends on the types of vehicles. There are a total number of 8 categories, and then we can go to chart number 2. Chart number 2 is numbers of vehicle corrections. One more point I want to remind you. All the correction factors here, the units is in terms of dBA. Okay, you just add them together. Okay, in this one, chart number 2, this is the corrections for the numbers of vehicles type. As I told you before, a single vehicle is composed of multiple vehicles. Okay, we call this one is a single vehicle. From A1.1, A1.2, and table A1.1, we just focus on a single vehicle. But for whole train vehicles, we have multiple numbers of railway vehicles. You may make use of this figure or this correction factor. Okay, 10 or n. Let's say if there are 10 vehicles, Okay, when you refer to this one, when you draw a vertical line and a horizontal line here, you can get the correction factor is 10 dBA. Okay, any problem? Okay, now we go to table 1. Table 1 is for the corrections for the trap form. In those questions, descriptions could be given to state that what kinds of trap forms is in those questions. For example, if this is a timber slippers, the correction factor is 0. If this is a floating slab trap, the correction factor is positive 2 dBA. Okay. Okay, now we completed the first two stages, stage 1 and stage 2. Stage 2 is to find out the sound exposure level, the reference level. Okay, now at stage 3, we have a total number of 6 corrections factors. The first one is distance corrections. Actually, this is very simple. We have two types, correct? Rolling railway vehicles and the diesel locomotive, correct? Before this one, the numbers of vehicles, I want to remind you, there is a remark here. For locomotive type, you need to consider this factor. But if this is for rolling type, you need to consider this factor. If this is a locomotive type, there is a remark here. Only a single locomotive is involved in most cases. So there will be no further corrections to be applied, okay, in this case. We have two types, correct? For rolling noise, we need to consider the numbers of railway vehicles. For locomotive type, we do not need to consider this one. Okay, because the power source normally is from a single car at the beginning. Okay, now we go back to the simplification. Because we have two types, A is rolling type, we consider that the source to generate the noise effects is at the interface between the rail and wheel, correct? Because this is rolling noise, so that the noise source is at the interface between the wheels and rail. So this is the effective source. Let's say the receiver is here. We draw a right angle triangle, and then we can calculate the direct distance between R and S, correct? And for the diesel locomotive type, we assume that the effective source position is 4 meters above ground. 4 meters above ground. So when you identify the source positions, you can still draw a simple triangle like this to find out the D pi here. Okay. So be careful. You have to read carefully about the descriptions in those questions. If this is a rolling type, we always assume that the effective source is at the interface between the wheels and rail. If this is a locomotive type, we assume that the effective source is 4 meters above ground. Okay, don't mess up this concept. Although nowadays we can only consider the use of rolling railway vehicles, not this one. Okay, once we got the values of d pi, okay, we can make use of these equations to find out the correspondence value. When you refer to this figure, okay, you can see that this point is 0 dB, okay? The distance is 25 meters. Why at 25 meters we set the correction factor is 0 dB? Because at the beginning, we assume that the microphone is 25 meters away from the rail track, okay? So that this is the reference point. If we assume that the reference point, the reception point is 25 meters away from the track, no correction factor should be applied for distance. But if the distance, the separation distance between the receiver and the effective source is longer than 25 meters, you can see that the correction factor, all the correction factors are negative values. It makes sense, the longer the distance, the lower the sound effects. So that the correction factors should be equal to negative values, okay? And this one, and this equation is exactly equal to this figure, okay? So that's either this equations or this figure could be given in final exam if there are relevant questions. Chart number 4 is for air absorption corrections. For volume type, we need to consider these effects. You may make use of these equations or these figures to find out the air absorption effects. Another remark here, please pay attention, no correction should be applied to noise level from locomotive type. For locomotive, it means that we do not need to consider the air absorption effects, okay? Chart number ground correction factor. Because this is a typical sections about the separations between the receiver and also the rail track, we need to study the ground corrections. If this is a concrete pavement, this is a reflective surface or absorptive surface. Reflective, correct? If another segment, this is a grassland, okay, with some plantations. This is an absorptive surface, okay, not reflective surface. So that's why this corrections is used to study the materials of the pavement, okay. For this one, if these two segments they are constructed by different materials, let's say segment A it is constructed by concrete structure, and segment B it is filled with some plantations. Okay, how to read this one? How to find out the ground corrections factor for this one? We use chart number 5. Please pay attention. Those equations are not equal to this chart. Those equations are not equal to this chart. This chart shows the corrections when I is equal to 1 only. When I is not equal to 1, please make use of the equation sets here. Okay, I'll repeat again. When I is equal to 1, we use this figure. When I is not equal to 1, we use this equation sets. What is the meaning of I? It means that the proportions of sound absorbing ground between the segments source line and the reception points. Okay, let's say when I is a pavement, okay, it's a concrete pavement. It means that the absorbing material is very small, so that it is very close to 10% I. I is just from 1. I is a parameter to describe the percentage of sound absorbing materials on this ground. Okay, it is in between 0 to 1 only. 0 to 1. In those questions relevant to this one, I could state clearly about the values of I. Okay, you do not need to guess what is the values of I. Okay, so when I is equal to 1, let's say we put some plantation, some absorbing materials inside these segments, we can make use of this charts. When you use the charts, another two parameters you have to find out is the first one is the FH height. How to find out this one? Please go to this one. There are two different cases. The first one is what we call the level ground. Okay, this is the effective source, volume noise, correct? At the interface between the rail and wheel. And let's say this is the reception points. Okay, we want to do the assessments. How to find out the FH height? The capital letter H is equal to HS. This is HS plus H divided by 2. This is a standard equation. And what is the values of hs? As stated in this document, they assume 0.7 meters. 0.7 meters. Okay. If I state other results, you can state clearly. If I do not state these results, you may assume it is equal to 0.7 meters. 0.7 meters. Okay. On the other hand, for uneven ground, like the situations shown in figure B, the values of the capital letter H is the summations of all this one. Okay, like this one. So that we have two scenarios to find out the values of H. Okay. Okay, now when we got the values of H, this is the values of H on the other side, right hand side, and the horizontal line here is the distance from the source line D. Okay, D. This is the D. What's D? This is D. Okay, distance, horizontal distance between the source and the receiver. Okay. Okay, now let's say the direct distance is 100 meters. Okay, and now we assume that I is equal to 1, and the values of H is equal to 4. Let's say is equal to 4. You can draw a vertical line here to intercept with this line, and then you draw a horizontal line here. The approximate correction factor is minus 0.7 dBA. Okay, this is 0. This is minus 1. So that's the value here is about 0.7, minus 0.7. Okay, now if I assume that I is equal to 0.5, not 1, okay, do not make use of this figure, okay, because this figure is just valid for I is equal to 1. In this sense, you have to make use of the figures of equations here, okay, to substitute the relevant values I, H, and D into the correspondence equations to find out the correction factor. Any problem? Okay, now Border's corrections, minus 1.5 dBA. What is the meaning of that? Please pay attention on this one. If there is only a single track, no matter this is a Border's form or a non-Border's form, you do not need to make corrections. Under what conditions and under what circumstances we need to consider this one is that we have two parallel tracks. We have two parallel tracks, track number 1 and track number 2. When you consider the presence of these double tracks to the receiver, we need to analyze the data one by one. Okay, you cannot directly analyze both of them together. If track number 1 is a Border's type, this is a Border's type. If this track number 1 is a Border's type, we need to consider minus 1.5 dBA for track number 2. Okay, why? Because when we generate a very noise source from this one to the receiver, it could pass through track number 1, correct? If track number 1 is a Border's type, it can help to absorb some portions of noise effects. We don't know what is the value. We just apply 1.5 dBA to this one. But for track number 1, we do not need to apply this one because the direct field is from S1 to R, okay? In between track number 1 and R, there is no any Border's effects. In another case, if track number 1, this one, is not a Border's type, what happens? We do not need to apply both minus 1.5 dBA to both tracks, okay? So that's the only conditions we need to apply minus 1.5 dBA to this case is that track number 1 must be Border's track, okay? I repeat again, this correction factor will only occur when we have a double tracks. If there is only a single track, we do not need to consider this factor, okay? Even this is a dual railway, okay? Double tracks. If track number 1 is not a Border's type, we do not need to consider this one, okay? Any problem? Okay, another one, screening corrections. The screening corrections, we may make use of these two figures, figure 1 and figure 2. Figure 1 is shadow zone and figure 2 is illuminated zone. Still, do you remember that how to identify this one? If we have a source, this is a source, and we have a receiver here. We draw a straight line, okay? We draw a straight line if this is a barrier to see whether the receiver is on which side, okay? Okay, I repeat again. Okay, this is source, this is receiver. If we install a barrier in between the source and the receiver, you draw a straight line along this one. If the receiver inside this zone, we call this is shadow zone, and we refer to this figure. If the receiver is above this line, we call this is illuminated zone. Okay, and then the path difference. How to find out path difference? Path difference. If this is A, this is B, and this is C, path difference is A plus B minus C. Okay. Once you got the values of path difference, let's say it is equal to 0.8 inside the shadow zone, you can draw a vertical line here, and then the correction factor is about minus 17 dBA in this case. Okay. Okay. Any problem? So that's the first step. The first step is to determine whether the receiver is inside the shadow zone or the illuminated zone. Okay. Otherwise, you cannot identify which figure you are going to use. Once you identify, let's say inside the shadow zone, you have to calculate the path difference. The path difference is very simple. Okay, just A plus B minus C. Okay, a direct calculation. And then you can identify it from the figure. When you refer to the scale here, all of them are negative values. Okay, it makes sense with the positions of barrier, so that's why the noise effects could be reduced. But if the receiver is inside the illuminated zone, you can see that the values should be much less than that compared to the shadow zone. Any problem? Okay, now we go to the real angle correction. This is the last correction factor for stage number 3. We have two cases. For the first case, this is a well track and this is the receiver. Okay. This is theta. Theta is the angle about this segments. Okay, theta is the angle for this segments. If we need to consider this segments, theta is the angle. How about the alpha? Alpha, this is the acute angle between the line. We draw a parallel line with respect to this track, and alpha is from this line to the bisection line of this theta. Bisection. Even theta is larger than 90 degrees in this case. How to determine the values of alpha is still from this parallel line to the bisection line of theta. Okay. once we can identify the angles alpha and angle theta, we need to find out the corrections factor. From chart number 7, please pay attention. This is all trains except diesel locomotive under full power. What does it mean? It is just for rolling vehicle, okay? For rolling vehicles, when you refer to this figure, this is the angle of wheel theta, and the alpha is here. This is theta, this is alpha. Okay, let's say if we take an example like this, if theta is 30 degrees and alpha is 75 degrees. You may directly plug these two values into this equation or to identify the results here. Okay, now the correction factor is 5.2 dBA. How to read this one? Theta is 30 degrees is here, correct? Alpha is 75 degrees. So that's you draw a line like this and find out the intersection points here. When you refer to this intersection points, this is -5 and this is -6. So that when you read the data from these charts, you may do a simple interpolations to find out the value is approximately equal to -5.2 dBA. Okay. This is 0.5, -1, -2, -3, up to -15. The point here is in between the lines -5 and -6. So that's why we can find out is -5.2 dBA, approximate value. Another way is that you directly substitute these two values into this equation. Okay, any problem? Okay, this is just for rolling noise type vehicles. And how about this one, chart number 8? Chart number 8 is valid only for diesel vehicles, okay? Diesel vehicle. The principle is still the same. We still need to identify the values of theta and alpha. Okay, what is the difference between this one? This figure I directly copied from the document, but I found that this equation is there is a typo in this equation. The correct form should be this one. Okay, this is the correct form to find out the values here. Okay, I repeat again. This figure I directly copied from the documents for your reference, and I checked that this equation should be this one, not this one. Any problem? So the only difference between chart number 7 and number 8, it depends on the types of vehicles only, okay? But both of them, you still need to use alpha and theta to find out the correction factors. Okay, now we go to stage number 4, is the reflection effects. For the reflection effects, there are two conditions or two corrections. The first one is the facade effects. Okay, let me explain this one. What is the facade effects? We are talking about the assessment points. Remember how to do the standard approach to do assessments. We always assume that the assessment point is 1 meter away from building facade. Okay, we could not do the assessments inside buildings. Okay, it doesn't make sense because all sound fields when it goes into the interior area, some of them could be absorbed and some of them could be reflected. So that this is not the real data to represent the real situations. So that's why we always keep this one. The assessment point is 1 meter away from building facade. So in reality, how to do the assessments? We extend a sound level meter 1 meter away from building facade. Okay. When we assume that this is the assessment points, you cannot guarantee that all sound fields can go to this assessment point, correct? Okay. Let's say this is a railway source, okay, rolling noise. When it generates direct fields to this assessment points, we cannot guarantee all sound fields can go to this particular point. It doesn't make sense, correct? Some of them could hit on these hard boundaries, correct? And then what happens? Reflections could occur. We don't know what is the level of this one, so that they propose that the correction factor is 2.5 dBA. And some standards, let's say in Hong Kong, we use 3 dBA. No matter you use 2.5 or 3 dBA, okay, this value is similar to each other. Okay, so this is what we call the facade effects, and we apply 2.5 dBA as the correction factor. Any problem? Do you understand this part? This point? Okay, the second point is reflections from opposite facades. Okay, let's say this is a track, correct? This is the assessment points, but on the opposite side, we still have some buildings. You may ask, under what conditions we need to consider the reflections from opposite facade, like this one? It depends on the real situations, okay? If all these buildings, they are far away from this rail track, we don't need to consider this one. If they are closer to this rail track, we may need to consider this one. How to consider this one? We use this corrections equation. In this corrections equations, it's 1.5 theta pi over theta. Theta is the total angle. And theta pi, what is theta pi? It's theta 1, theta 2, up to theta 4, okay? We just consider each angle. And then you can find out the reflections effects. Okay? As I told you before, we need to consider the real situations, okay? I cannot give you real factors or real distance. Let's say 10 meters, we need to consider this one. More than 10 meters, we don't need to consider this one, okay? It is hard to identify this one. It depends on the real situations, okay? Sometimes, if you define or you can judge that those buildings, they are closer to these assessment points. To be conservative, you need to take it into consideration, okay? Okay, so that's the first one for side effects is from the assessment points, okay? And from the reflections from opposite facade, we are talking about that on the other side along this rail track, okay? Okay, do you still remember that at the beginning, stage number 1, we need to consider that whether we have to derive into different segments, correct? Okay, in this case, we have a single track. Do you consider that whether we need to consider we need to derive into different segments, or we just consider that this is a whole segment? In this case, when you consider this figure. Okay, there are several conditions. If we encounter one of them, we need to derive into different segments. Now, let's take a look on this one. Here we have a reflective barrier, correct? This barrier could block those sound effects generated from this rail track to this reception points, correct? But on the other side, we don't have a barrier. So in this case, at least we have to derive into two segments. One is this one, alpha 1. Okay, this is the first segment. And the second one is this one. This is the second segment. Okay, the first segment with the provisions of effective barrier. On the other segment, this one without a barrier. So in this case, reference to this figure, at least we have to derive into two different segments. Any problem? Okay, now go to stage number 5. For the stage number 5 is that we have from stage number 1 to stage number 2 to stage number 4, we are calculating the sound exposures level, not LAEQ. Okay, but at stage number 5, we have to convert this value SEL to LAEQ. How to convert it? It depends on two scenarios. It depends on two equations. The first equation is from the night time, and for the second equation is from the daytime. We just have a single sound exposures level value. Q here is the total numbers of trains passing through the reception points during this time period, and Q day here is that the total numbers of trains passing through these reception points during the daytime. Okay, you just plug in the correspondence values, you can get back the results. And finally, if we just have a single segment, we can directly get the overall results. If we have multiple segments, how to consider this one? You may simply consider that multiple segments, let's say in this case, we derive into two segments. They are two sources. Okay, let's say if we have two segments, one contributes 72 dBA and the other one is 74 dBA. What is the total level? Still, do you remember that? How to add them together? In this case, we can make use of this one, correct? Okay, this is the standard equations to add two sources together. Okay, you can refer to your first lecture. This one, correct? Actually, we can make use of this figure directly because when you refer to this document, many corrections factors we can directly read from the figures or charts rather than we need to do some calculations. Okay, now how to make use of these figures? Take this as an example: 74, 72 dBA. We have two values. Okay, so the first step you have to find out the difference between them. The difference is 2 dBA, correct? 74 minus 72. When the difference is 2 dBA, the corrections factor here, what is this one? It's about 2.1 dBA. Please just add these corrections factors to the highest one, to the highest value. 2.1 plus 74 is 76.1 dBA. This value is exactly equal to this one. You do not need to do any calculations. Okay, you can directly read the figures to find out the overall effects. Okay, now if we have two segments, we can make use of or the calculations as the example like this. How about if we have three segments? Okay, the first one is 72, the second one is 74, and the last one is also 74. Can we make use of these figures to find out the overall result? Yes or no? Okay, let me show you how to do this one. First of all, we consider this two. What's the result? 72 minus 72 is 72 is 2 dBA, and the overall value is 76.1, correct? And then you compare 76.1 and this one. Okay, 76.1 minus 74 is still equal to 2.1. Okay, is equal to 2.1. When you refer to the data here, the correction factor is about 2 dB. Is about 2 dB. And then what is the next step? Okay, no matter we have multiple segments or multiple data, you can consider one by one. Okay, any problem? Okay, you can make use of these equations to check this example together. Okay, this three data to find out the overall level to see whether you can get this one. Okay, let us take a 5 minutes break and then we will go for tutorial number 4 together. Okay, now we go to our tutorial parts. Because of the time limits, I will go through and explain the answers to you first, okay? And I will share the answers to you later on. If you have any problems, you may ask me. For the very noise control, noise control, in the coming two tutorials, I will have some relevant questions to you, so that at that time, you may have a better understanding how to make use of these documents for petitions, okay? So, and in this lessons, my target is just to share with you that the basic principles to that. And remember, all the corrections factors here, they are expressed in terms of dBA, okay? Not dB, dBA. We could only make use of dBA for assessments, environmental noise assessments, okay? Okay, I already uploaded this tutorial questions to you. Let's go through together. And these tutorial questions, they are relevant to our previous lecture, topic number 3, publications, some publications and some events. I just want to let you know how to solve this one. Okay, the first one, for the first question. Okay, we have a plant room for an air conditioning fan. The area is 4 meters times 3 meters, and the height is 2.5 meters. It has 4 brick walls, a concrete floor, and a steel deck. Roof having 15 millimeter thickness of glass fiber, and an aluminum finish to the underside. We can ignore the effects of the metal plant air ductworks and the door into the plant room. Calculate the room constants. This is the room constants and the reverberations time for this room at 125 hertz. You may refer to the absorption coefficients in these tables, okay, from 125 Hz up to 4K Hz. This questions type is similar to your assignments questions and even in your final exams. And so that I want to give you more examples for your practice. For the first questions, we need to find out the room constant. Please bear in mind that there are two questions. The first one is to identify the room constant, and the second one is to determine the relevance reverberations time. Okay, let's do it together. Okay, this is the dimensions for the room, and you can see that the absorption coefficients for the wall, concrete floor, and steel deck roof. You can refer it from the table. First of all, we need to find out the floor area, ceiling area, wall area. Why we need to do this one? Because we want to find out the surface area, total surface area, and then we still need to calculate the volume of this room. Okay, the volume of this room is 30 meter cube, and the total surface area is 59 meter square. Okay, why we need to do this one? Because these two parameters are relevant to the calculations of reverberations time. Okay, now we just consider in this question is 125 hertz, so that's why we just look at this column. Now the floor, we select these 3 parameters: brick wall, concrete floor, and the ceiling is 15 millimeter glass fiber. Okay, we select the appropriate conditions. Okay, so that's this one, concrete is the floor absorption coefficients, brick wall is the absorption coefficients for the wall, and this is for the ceiling. And the room absorption is the summations of each of them. So that you can find out that the room absorption is 3.79 meters square Sabrine. Okay, some of them could ignore Sabrine. Okay, just write it as 3.79 meters square. Please pay attention. This is not the geometric area. This is the room absorption. Okay, now when we got this value, we can find out the FH absorption coefficients. For the FH absorption coefficient is the total one divided by the total surface area. It is equal to 0.064. Okay, when you refer to this figure, what does it mean? It is reflective or absorptive? It is highly reflective. Okay, because it is closer to 1, closer to 0. Okay. Okay, now for the room constants, this is the standard equations. We know that A is equal to 3.79 and the FH solid absorption coefficient is 0.064. So that's why room constants is 4.05 meters square Sabrine. Okay, and how about the reverberations time? For the reverberations time, actually, the lower part, this is equal to A. Okay, and the upper part is 0.16 times volume. So that's at 125 hertz. The reverberations time is up to 1.27 seconds. You can repeat those procedures to find out the values for other frequency values. Okay, any problem for question number 1? I think that this is not so difficult. Okay, we just follow the standard equations and approaches. We are able to find out the final results. Any problem about this one? Okay, for the second problem, for the second and the third problem, it is relevant to transmission loss. Okay, transmission loss. It is talking about what is the behavior of the materials to isolate the acoustic energy. Okay, this is the standard equations to find out the transmission loss, and the parameter here tau is it refers to the transmission coefficients. Okay, remember this one. And there is an equations here I explained to you before. Let me show you an example how to do the calculations for using this one. Okay, now the situation is like this. We have a concrete wall. We have a concrete wall here. The concrete wall here is 10 meters times 3 meters. Okay, these are the dimensions of this wall, concrete wall. Now, on this wall, there is a closer window. This is a closer window and a sealed door here. Okay, so in total, we have 3 components. Okay, door, window, and wall. Correct? Okay, now the transmission loss of the sealed door, this one is 26 dB. So that when sound wave passes through this door, the transmission loss is 26 dB. You can isolate 26 dB acoustic energy. Okay, and the transmission loss of the closer window, this one is 29 dB. 29 dB. Because different materials, they have different transmission loss. Okay, so in this situation, the overall transmission loss, what is 32 dB? What does it mean overall? Overall, it means that the FH transmission loss, FH value. Okay, now if there is a circular air opening and the opening with a radius of 0.1 meters created on this concrete wall, what is the change of the overall transmission loss? Okay, the scenario is like this. We create an opening here. Okay, so the original is this situation. Now we go to this situation. Originally, we just have 3 components: door, window, and wall. Now we have 1 more component, air opening. Correct? Okay. When we create a hole, an opening, it means that there must be a change of transmission loss. How to calculate this one? First of all, the overall transmission coefficients in the original situation. is 32 dB. Transmission loss is 32 dB, correct? So when we consider these equations, the transmission coefficient is equal to 6.31 times 10 minus 4. Okay, we just do a simple conversion. What is the usage of this one? Because we want to find out the transmission coefficients of the wall. When you go through details about the descriptions or expressions, we do not know the values of the wall, the transmission loss of the wall. Okay, we only have the values for the door and the window. How to find out this one? Okay, this is the FH coefficients of the wall or the overall situation. This is the FH1. And what is this one? 30. 30 is the total area. Okay, because this is 10 meters, this is 3 meters. What is the total area? 30 meters. This is the total area, and this is the FH coefficients, transmission coefficients. Now, for the wall, this is for the wall. We don't know this one, so that we have to find it out. How about this one? Why we need to use 30 minus 0.75 minus 3.75? Because this is the net area of the wall. Okay, you have to deduct the area for the door and the area for the window. And the second one is for the window. The window area is 0.75 meters square. And how about this one? Because the transmission loss is 29 dB. Okay, transmission loss is 29 dB, so that's why you can write it into this form. And the last part is for the door. The transmission loss for the door is 26 dB. Okay, so that's why we can make use of the door area times this one. This is the transmission coefficients for the door. Okay, now we just have one equation and one unknown, so we can find out the transmission coefficients for the wall is 3.36 times 10 power to minus 3. Okay, any problem so far? Okay, now we go to the new scenario. Now we have an opening here. When we have a circular air opening, what is the area for that? The area for that is very simple, is pi r square. Because r is just 0.01 meters, so that's why the area is this one. Okay, now please consider. Now we have to find out the overall, or what we call the FH value. The total area is still 30 meters square, correct? Even we make many holes on the wall, the total area is still 30 meters. Now, for the first one, this is for the wall. Okay, this is the total area. You have to deduct the window area, door area, and also opening area. Okay, any problem? For the second part, this is just for window. For the third part, this is for the door. We still need to cater for the air opening. For the air opening, the area is equal to 0.0314. How about the corresponding coefficients? Why it is equal to 1? Because the transmission loss in the opening is equal to 0 dB, okay, no any loss. All sound fields can pass through this opening, correct? So that's why the correspondence values is equal to 1. Okay, now, make use of our calculator. We can find out the FH the FH transmission coefficients. It becomes 1.68 times 10 power to minus 3. Okay, anything is unclear about this one, how to construct this equation? Okay, now we haven't finished because we still need to find out that what is the change of the transmission loss. So that the corresponding overall transmission loss based on the new value is 27.7 dB. So the final result is that the change of the overall transmission loss is minus 4.3 dB, minus 4.3 dB. This one, without the creations or an opening, is 32 dB. If we create a hole, it becomes 27.7. It means that the transmission loss can be reduced. It makes sense because you know that with an opening, more and more sound energy can pass through it. So that's why the ability of transmission loss could be reduced. Okay, any problem? In the whole example here, we just make use of this equation and also this equation only, these two equations only. Okay. Okay, final questions. Now, this is also relevant to transmission loss. But in this case, we do not need to do any calculations because reference to these questions, I request you to find the answer from this figure only. Okay, from this figure, we have two components. And exterior wall, it has transmission loss of 49 dB at 1 kHz. And we have now we have two windows on this wall, and each of them is 3 feet times 4 feet with single glass 3 mm with a transmission loss of 34 dB at 10 at the same frequency. Okay, we do not need to do any calculations for this one. Let us try to read through this one, how to read out. First of all, when you refer to this figure, it explains to use that if we have two components, S1 and S2, we need to find out the horizontal axis refers to the transmission loss for the first components minus the transmission loss for the second components. For this one, for the vertical axis, this is TL1 minus TLC. TLC it refers to the combined transmission loss. In this case, TL1 minus TL2 is 49 minus 34, correct? Okay, it becomes 15 dB. 15 dB is here. Now we need to find out the ratio. In this one, please bear in mind that we do not need to deduct the net area. Okay, S2 it refers to the window area. We have two windows, so that it is equal to 2 times 3 times 4. Okay, and how about S1? S1 is the wall area. Wall area is 8 feet times 16 feet. So that the ratio here is approximately equal to 18.8%. Okay, you draw a line here because TL1 minus TL2 is 15 dB, and the ratio as percentage of the total area is 18.8. Is here, about here. Okay, this point. This is 20. This is 10. So that 18.8 is here. So that's why we can get the data for TL1 minus TLC is approximately equal to 8 dB. 8 dB. We know the values for TL1 because TL1 is 49 dB. So that's why we can get the final result is 41 dB directly. It means that the overall, or we call this one is the average transmission loss, is 41 dB for the whole components with the concrete wall, with the brick wall, and also our glass window. Okay. So in the third questions, we just with the data from the figure rather than we do any calculations. Okay, I will send back all these solutions for your revisions later on in the next week. Okay, if you have any problems about that, you may ask me. Okay, thank you.